Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last lecture, we started discussing the bonding in hydrogen molecule. In particular, we are looking at the valence bond treatment of hydrogen molecule, which we described as an application of variational principle that we have discussed. In this treatment, in the valence bond treatment of hydrogen molecule, we have defined our guess function phi or the trial function phi as linear combination of two functions psi 1 and psi 2, where psi 1 was defined as the product of two functions, one is A, where the function psi 1 was defined as electron 1 from corresponding to nucleus A multiplied by electron 2 in the 1s orbital of nucleus B. This was psi 1, and we also said that since the electrons are indistinguishable in the molecule, so therefore, when the molecule is forming, hydrogen molecule is forming, in that case electron 1 and electron 2 should not be distinguishable. So therefore, we wrote down psi 2, where we assigned electron 2 to 1s A orbital and electron 1 to 1s B orbital, and then we said, okay, let the trial function phi be a linear combination of psi 1 and psi 2. Since psi 1 and psi 2 are known, only unknowns are now C 1 and C 2, and since we have described our trial function as a linear combination of two functions, then the linear variational principle tells us that we have to solve this 2 by 2 problem, 2 by 2 matrix, where the matrix elements are given here. In the last class, we discussed the overlap integrals S 1 1, which turned out to be 1, which is similar to S 2 2, and S 1 2 and S 2 1 turned out to be S square, which is nothing but the overlap integral between the 1s orbital of atom A and 1s orbital of atom B. So, in today's class, what we would do is that we will look at the other terms in this equation and see how we can obtain them. So, since we have already determined the overlap integrals, what is unknown is now these energy integrals, and that is what we would discuss now. First topic would be to find out this energy integral corresponding to H 1 1. Just to remind you, this is my Hamiltonian. The Hamiltonian of hydrogen molecule is given by these terms. So, the first two terms together show the kinetic energy of electron 1 and the electron 1's interaction with nucleus A. So, this corresponds to the Hamiltonian of A hydrogen atom. The second term tells the kinetic energy of electron 2 and its interaction with the nucleus B. So, therefore, these two terms together represent the Hamiltonian corresponding to hydrogen atom B, and these 2A 1B are the interaction of electron 2 and 1 with respect to nucleus A and B respectively. So, these terms do not appear when the two hydrogen atoms are far away from each other, but when they form a molecule or when they form a bond, these operators start appearing. Similarly, when the hydrogen atoms are far away from each other, their electrons do not have any interaction between them, but once they come closer, the electron repulsion appears, and similarly the two nuclei also start repelling once they come closer to each other. When the two nuclei are very far away from each other, these terms starting from the last 5 interaction energy terms, last 4 interaction energy terms, they disappear when the two hydrogen atoms are far away from each other. Now, when we are looking at the energy integral H 1 1, so H 1 1 is the matrix element corresponding to psi 1. So, this is what we have to evaluate. This is the now, in other words, what we are going to do is that we are going to write down this psi 1 star. So, since psi 1 is written over here, psi 1 star is simply the complex conjugate of psi 1, and then we have this psi 1 again the wave function, and then we are integrating it over dr 1 and dr 2. So, now what we do is that we evaluate these energy integrals. To do that, so we see that we have the psi star, we have psi, and this place that we have is the place for the Hamiltonian operator. So, once we have the Hamiltonian operator here, this is psi 1 star, this is psi 1, and this is energy integral H 1 1. Now, look at this the Hamiltonian. The first two terms, as I said, represents the hydrogen atom A. The hydrogen atom A Hamiltonian, the solution of this is simply this. The eigenfunction of this Hamiltonian is 1sa1 with an eigenvalue of minus 0.5. Similarly, the Hamiltonian corresponding to hydrogen atom B, its eigenfunction is 1sb holding electron 2 with an eigenvalue of minus 0.5. This minus 0.5 is coming because that is the ground state energy of hydrogen atom, which is half atomic unit. So, now we have these two terms, the Hamiltonian of A, the Hamiltonian of B. So, let us first try to, instead of putting all the terms over here, first let us look at what happens when I put this Hamiltonian, the first two terms, into my this integral. So, I am first looking at this H A contribution of H A term, the first term, this Hamiltonian, and when I look here, I see that H A, the Hamiltonian of corresponding to nucleus A, has 1s_a1 is its eigenfunction. So, when this Hamiltonian acts on this 1s_a eigenfunction, the result I would get is minus 0.5, which is a constant, multiplied by 1s_a of 1. Let us write that down. So, I said minus 0.5, which is a constant. So, I brought it out, and then I am left with so this Hamiltonian is gone because it has already been applied to 1s_a1, and I result is minus 0.5 into 1s_a1, because this is an eigenfunction of this Hamiltonian. Now, when you look at this term, see this integral has some terms corresponding to electron 1 and some terms corresponding to electron 2. So, we can separate the terms which have dependence on electron 1. So, there will be these three terms 1s_a star, 1s_a, dr1, and you remember that 1s_a is an eigenfunction of hydrogen atom A, how the Hamiltonian is an Hermitian operator. So, this is this function is a well behaved function, and we can always normalize, and if this is normalized, the integral corresponding to dr1 would become 1. And similarly, when I look at the terms that have dependence on electron number 2, 1sb star, 1sb, dr2, when I integrate them, that also will give me 1. So, therefore, as a whole I will get minus 0.5 as the answer. What is it? Where this is the value I am getting when I am using only H A from this Hamiltonian, but remember we have many more terms to look at. So, instead of H A, suppose I consider now H B. When I consider H B, so I simply have to replace my H A with H B. Now, when I look at H B, I see that H B is no longer so this 1sb2, this function is actually an eigenfunction of HB2. So, this operator will now act on 1sb2 because this HB Hamiltonian, I see that since we have defined this Hamiltonian in terms of electron number 2. So, the operators are actually dependent on electron number 2. So, they will have no dependence on 1s_a function here, since 1s_a function now depends on electron number 1. When I do this, I would have something very similar. What would I get? Since HB, when HB acts on 1sb, I would actually get minus 0.5 into 1sb2. So, in fact, I would get exactly the same term. So, 1s_a star, 1sb star, these two terms are there, and when 1s_a1 remains unchanged here, 1sb2 I am getting, because when Hamiltonian HB acts on 1sb function, I get minus 0.5 1sb, and when I integrate this function again, I will get minus 0.5. So, this term gave me minus 0.5, this term gave me minus 0.5. So, together I have already obtained minus 1. We will keep that in mind, and now we will look at the the rest of the terms. So, to do that, let us clean our region over here, because now we will start looking at the other operators and how they influence how we are getting this integral. Let us now consider 1 over r 2 a. What is 1 over r 2 a? This is the distance, this operator corresponds to the distance between electron number 2 with nucleus A. Now, since we are working within Born-Oppenheimer approximation, so therefore, the nuclei are frozen. So, therefore, this term that we have, this operator term, has only dependence on electron number 2. Now, what we will do is that we will evaluate the will express this integral in terms of electron number 1 and electron number 2 terms. So, let us do that. So, I have the first term 1 s a star, this depends on electron 1, this function depends on electron 2. So, let us write that separately. What about the operator? The operator is 1 over r 2 a. So, that depends on electron number 2, and then 1 s a 1. So, this is a function which has dependence on electron number 1, 1 s b 2. This is a function which has dependence on electron number 2, and now I have the integrals dr 1 and dr 2 I write in this way. Now, when I look at the first term, I see this is normal, 1 s a is normalized function. So, this becomes 1. What about this term? This term, mind you, this 1 over r 2 a term has actually a minus sign. So, let us use this minus sign over here. So, this term becomes 1, and now I am left with the second term, which is this kind of term. Now, if we look carefully this term, what does this say? This tells me when I have 1 s b to a mod square, this is actually the probability density corresponding to the electron number 2 when it is with nucleus p. So, that means this term with the negative charge, negative sign, together it says what is the electron density distribution corresponding to electron number 2. But when I look at this 1 over r 2 a, this would remind me that this term is essentially the interaction between two things. One is the electron density corresponding to electron number 2, which is under the influence of electron B, and the interaction of this electron density with the nucleus A. So, now I have this term which is expressed as a Coulomb interaction term, where the two charges are in the Coulomb interaction term are the following. One is the nucleus A, and the second is the electron density distribution corresponding to electron number 2. Why do I call electron density distribution? Because I have this 1 s b 2 star 1 s b 2 mod square integrated it over dr 2. So, that will give me the distribution of the electron density over all space. So, how electron 2's electron density is interacting with nucleus A. So, this term gives me 1 Coulomb integral term. Similarly, if I consider instead of writing 1 over r 2 a, I would consider a term as the next term minus of 1 over r 1 b. What would I get? I would get a term, if you do this, I would get a term which will look like, let us do that as well. I would get a term which will appear as, so in this case I am looking at r 1 b. Now, when I try to solve this integral, I see the operator depends on electron number 1. So, therefore, the integral that I would have is 1 s a star Now, this function is this term is going to be 1 because 1sb is a normalized function, and when I look at this term, this also resembles another Coulomb integral. In this case, what is this term? This term can be expressed as the following. This term indicates the electron density distribution corresponding to electron number 1 and its interaction with the nucleus B. This term, when we had R over 2a, this term said about the interaction between electron density of electron number 2 with nucleus A, and this term is telling the electron density distribution of corresponding to electron 1 and its interaction with nucleus B. So, we would now what we would do is that we will look for the next term. Next term is 1 over R 1 2. So, when I look at 1 R over 1 R 1 2, I have no negative sign here. So, R 1 2 and 2, when I evaluate this integral, what do I see? I see now my operator, unlike the first two cases, the operator R 1 2 now depends on both the electrons. So, therefore, I cannot separate this integral into R 1 terms and R 2 terms because the operator depends on both the electrons. So, when this is the case, I can write this as simply 1 S A star 1 S A, which is now what does this term tell me? This term tells me the 1 S A star 1 S A square is electron density, negative of this is electron density distribution corresponding to electron number 1, and negative of this term is the electron density distribution corresponding to electron number 2. When I multiply them, that means when I look at their Coulombic interaction, so 2 minus signs become plus. So, this term as a whole tells me the Coulombic interaction between the electron density of electron number 1 with that of the electron number 2. So, therefore, I am left with this term over here. And now finally, so this is again one more Coulomb term, and finally, I have this term left in this Hamiltonian, which is 1 over R A B. Now, this operator does not have any dependence on either electron 1 or electron 2, because this is a constant when it comes to the electronic coordinates. So, therefore, this term when I plug this in this integral, so this term is a constant, it will come out, and then I have the set of normalized function. So, it is easy, you can do it for yourself, and then you would see that this is simply 1 over R. Now, what is 1 over R? This is Coulombic interaction between the two nuclei. Now, what we have got in this H11 is, just to remind you, the first term gave me minus 0.5, this Hamiltonian HA, this term gave me minus 0.5, and now I am left with some Coulomb integrals. So, I call them together as a function J, which will have dependence on capital R. Why is it so? You see that of course, there is a straightforward definition dependence of 1 over R, but even without that, all our electronic Hamiltonian that we have defined is with respect to a particular distance between the two nuclei. So, therefore, this Coulomb integral, the value of this integral will keep changing when you change the distance between the two atoms. So, together what we have got is that we have this term as minus 1 plus j of r, where this j is the Coulomb integral. So, now we obtain what is the value of H11, and similarly you can show that H22 is also having the same value. So, that is minus 1 plus j of r. So, when you do H22, your bra and ket function will be psi 2, and your operator will be something this Hamiltonian. So, now we learned what is H11 and what is H12. We still have one more term left, and that is the H12, and that is what we would go to discuss next. when we look at H12 term, when you have H12 term, we have psi 1 star. So, H12 is simply psi 1 star, the Hamiltonian psi 2 and integrate it over all space. So, psi 1 is given, psi 2 is given. So, we have to find psi 1 star Hamiltonian psi 2 and this is the Hamiltonian. So, my psi 1 star here, psi 2 here. Now, the place that I have left here is for the Hamiltonian, but one thing you notice here, the Hamiltonian, as we saw in the previous case, the operators that we are writing here, they are first applying to the function there that are in the right hand side. So, therefore, I must look at the functions that are there in the right hand side. When I look, I see that the function, because this is psi 2, so electron 2 is with nucleus A, electron 1 is with nucleus B. When I look at this 1sa2, I see that this will be an eigenfunction of a hydrogen atom, but what would be the nucleus? Nucleus would be A, and what would be the electron? This will be the electron corresponding to electron number 2. So, if I construct a hydrogen atom by taking electron number 2 and nucleus A, this function will be an eigenfunction of that Hamiltonian. So, let us find that out. So, I want the electron number 2 kinetic energy operator. So, this is over here and its interaction with nucleus A, these two terms when I consider, I see these two terms together, this operator will have this as an eigenfunction. Similarly, 1sb1 corresponds to a function where electron 1 is under the influence of nucleus B. So, I see that these two terms together, this corresponds to the kinetic energy of electron 1 and this term is potential energy of interaction between electron 1 and nucleus B. So, therefore, this function is going to be the eigenfunction of this operator. So, once I would now again like the previous case, I would first take the first term, I call this as HB, let us call this HB giving by noting the nuclear, giving the nuclear identity. So, when I have this HB term over here, you see this will be acting on this function because this has dependence only on electron number 1, and similarly when I do that, I would see that since 1sb is an eigenfunction of Hb with and the eigenvalue is minus 0.5. So, again I write down the terms that have electron number 1 dependence. So, Hb when it acts on 1sb of 1, it will give me 1sb1, I integrate it over dr1 and then I write down the functions that I have corresponding to electron number 2. Now, when I look at this term, what do I get here? I get here the overlap between 1sa and 1sb. We have seen this term when we were determining S12 overlap integral. So, this term is not going to be 0 because these are eigenfunctions of two different hydrogen atoms, 1sa and 1sb. So, therefore, they will have some finite value and their value will depend on the internuclear distance and we had already defined them as S. Similarly, this term will also have an overlap integral S and together I will get this as minus 0.5 S square. I can also show the same value when I consider this Hamiltonian. Let us consider this Hamiltonian A and I would see that this also will give me minus 0.5 S square. So, together I got minus S square because minus 0.5 S square from this term, minus 0.5 S square from this term, together I have minus S square term and I still have not evaluated what are these terms, So, now we do the we do that part. So, we will just change the operator that we have in this integral and use the other terms that we have not considered yet. So, since we have taken care of R1b and R2a, the other two interactions between the electron and nuclear are going to be R2b and R1a. So, let us consider first this term minus 1 over R2b. When I say this operator will have explicit dependence on electron number 2. So, what I can do is, for example, I can separate now the integral corresponding to electron number 1 . And since the operator depends on electron number 2, I have now when I look at this term, this kind of term I have already seen, but let us focus on the second term. When I look at this second term, I see the wave functions that I have, one is B star 2 or one is 2, they are actually the wave functions of two different hydrogen atoms, both carrying electron number 2. So, unlike the previous case, I cannot express it as a Coulomb integral, because this is not no probability density expression. So, therefore, this term will not have a simple physical interpretation. And why am I getting this term? I am getting this term because I have this psi 2 which I have obtained by exchanging the electrons. So, this integral that we are getting does not have any physical description, unlike the previous case Coulomb integral, and we are getting this because we have done the electron exchange. Similarly, you do that when you plug 1 over R 1a or 1 over R 1 2 or 1 over R a b, you would see that you will get some integrals who would not have any physical interpretation, and together we will call these integrals, the sum of all these integrals, as an exchange integral, which is of course going to be a function of nuclear coordinate. So, this k is now our exchange integral. Now, similarly, you can show that H21, so we obtained H12, we can show that H21 is also going to be having the same value. So, now we have determined the values for all these terms. So, let us look at what we have achieved so far. We have seen that we started to we wanted to solve wanted to diagonalize this problem, this 2 by 2 matrix, by evaluating the matrix elements. So, we have obtained the matrix elements that we wrote down previously. Now, what we have done is that we have used H11 as minus 1 plus j, H12 as minus s square plus k, H21 and S22 similarly, S11 or S22 are 1, S12 and S21 are s square. So, now we have used in this expression, we have applied the integrals, the values that we obtained from our previous exercise, and now we have this 2 by 2 matrix. When we diagonalize this 2 by 2 matrix, we would see that the two energies, the eigenvalues that are coming out will be E plus and E minus, because this is a 2 by 2 problem. So, therefore, the solution we are going to get two energies. So, one is E plus, another is E minus, and you see that they are related to each other. I have the first term is minus 1 plus some other term. So, other terms have Coulomb integral, exchange integral and overlap integral, and I can determine these values of Coulomb integral, exchange integral and overlap integral at different value of internuclear distances. What you should see here, what is this energy? This is the energy of hydrogen molecule. Now, when I look at this energy expression, I see that the energy has a minus 1. This minus 1 tells me that hydrogen molecule, for example, when I bring this hydrogen molecule and I form this bond between them, this is different with respect to the two, when the case when the two hydrogen atoms are far away from each other. When the two hydrogen atoms are far away from each other, each of the hydrogen atoms ground state energy was minus 0.5. So, together their energy was minus 1, but when I bring them together, then they start overlapping and then the energy changes. If I have to plot this energy, so let me call this function as delta E plus or delta E minus, which is essentially the energy or the binding energy or the bond energy that is arising when the two hydrogen atoms interact. So, if this is my okay, if this is my energy E plus or E minus, I would see that, and this is my r axis, the internuclear axis, at very large value of r, of course, these terms will become 0. So, therefore, the energy, the two energies, if I have to plot, they would look like this. So, this is E plus and this is E minus. You would see that and these are for different values of r. Of course, for at very large value of r, the two energy would be equal to each other, and when the two nuclei come closer to each other, then I would see only the E plus will develop a minimum, and this energy is your stabilization energy or the bond energy that we get by forming this hydrogen molecule. Now, the wave function that we have here, once we have the eigenvalues E plus and E minus, we can plug this E plus into this expression and obtain the eigenvectors, and the eigenvectors are essentially will give me C1 and C2s, and when I obtain that, I am not doing this in this class, it is easy for you to do it. I would see that the two wave functions psi plus and psi minus are given as this. So, the two wave functions, the eigenfunction corresponding to E plus is simply psi 1 plus psi 2 multiplied by this constant, which is a normalization constant, and corresponding to E minus, the function is psi 1 minus psi 2. So, since we already know what is psi 1 and psi 2, so therefore, we also know now the eigenfunctions or the wave functions of this hydrogen molecule. So, in today's lecture, we discuss the bonding in hydrogen molecule via valence bond treatment, and we see that how we can use variational principle to determine the to describe the formation of a chemical bond in hydrogen molecule and what are the corresponding wave functions. Thank you for your attention.